So this is a work about attention layers, and actually we have started discussing this with Pierre Marion a few years ago because we were frustrated to see that there was a few mathematical analysis of attention-based layers that could explain the tremendous performances of those architectures for very, very different tasks. Okay, so after a few years of discussion with Pierre and a few existential crises, we managed to define a new statistical task for which attention layer will be good to solve it. Okay, so this is a joint work, of course, with Pierre Marion, and then Raphaël Berthier joined us on the road, and of course with the one and only Gérard Biot that has just been elected member of the Academy of Science in France. So we can give a round of applause for these exceptional colleagues. Great. Okay, so attention layers are actually a basic element in transformer structure. Okay, so transformer are, as you may know, neural network architecture and correspond to the T in the ChatGPT here. And to understand their kind of statistical flexibility, we have defined this single location regression. Okay, so the single location regression is inspired by NLP, natural language processing, but of course I need to make some disclaimers because we are doing a lot of simplifications in this statistical model. Okay, so we are in the classical framework of supervised learning. Okay, but as we are interested or inspired by NLP problems, we will assume that our input X is actually a sequence of tokens. Okay, and in this talk, I will make the confusion between tokens and words, even if it doesn't correspond to what is done in practice. Okay, so for me, a token is equal to a word, which is wrong. Okay, so each XL will be assumed to be a d-dimensional vector. Okay, so this is some particular embedding of the word of the token, and we can then consider that X is actually a sentence made of words of tokens. Okay. So I will actually add a bit more of hypothesis here, like restriction actually. We will assume that this input is a sequence of L random and independent tokens. Okay. Okay, and of course we are doing regression, so we also have an output here. And our output is a real quantity. Okay. So let me define now the learning problem that we are looking at. So we will assume that Y is linked to the input X in the following sense. Okay, so I have a particular token in my input sequence that should be used in combination with some regression vector V star to produce the output Y. Okay, so G0 is therefore a random variable on 1L, okay? It's a random index that chooses a relevant token to form the prediction of Y in a linear combination with V star, okay?
And the X is not random anymore after the J is fixed? Or
yeah, so I need to precise how I construct the input sequence, yeah, indeed. So G0 is a random variable on the set of indices, and we will assume that conditionally on G0, so xg0 follow follow this Gaussian distribution, okay? So a line centered in K star, some parameter K star, with a scaling factor here in the dimension of the input, and a covariance matrix proportional to the identity, okay? And of course, for all the other tokens, we will assume that there is no particular information, okay? So this is just a random Gaussian vector. So it means that for each sequence, input sequence, the relevant token for my prediction task is actually the token that is the more aligned with K star, the parameter K star. But of course, K star and V star are unknown, and they are the parameters of my model, okay? And I will assume that both belong to the sphere, okay? Okay. So the challenge here is, of course, to detect first the relevant token for the prediction task. And then, once I know which one is a relevant token, I have to fit a linear model, right? Okay.
So does J0 depend on the instance, or is J0 the same for all the instances?
No, it depends on the input sequence. Each input sequence has its own G0. Yeah, of course. Otherwise, this will be too easy. Yeah.
Just to make sure, so like in the model, you train a model on a sequence of n, like a set of n sequences of L tokens.
No, okay. So in the supervised learning setting, I will have pair of xi, yi. Okay, so I should say, I would do this right now. Yeah. Okay. So I have pairs of input sequences of tokens and output, and I try to learn something about it.
So you observe n matrices of size d times L.
Yes, exactly. Okay. Sorry? Okay, so thanks for this question. I want to make a remark about it. So why is there a gamma here? So since there are plenty of statisticians in the room, I'm happy that gamma is here, because you could have the following remark saying that this task can be easily solved, right? How could we do it? We could just look at the norm of the token, right? So if I do this in expectation, when I'm not a relevant token, so when I'm different from from the index G0, this is equal to D, of course. And when I am the relevant token here, I obtain this. Okay, so then, not to be in favor, not to help me with this task, I will choose gamma squared to be 1/2. Okay, so that I cannot distinguish like the relevant token with a simple test. Okay? Is that clear? Yeah? Okay. Okay, so it means that with this choice, the magnitude of the token is not informative for my task. Okay? And another way to rephrase this task could be to say that I'm actually doing a one sparse regression, but the support of the sparse coefficient is moving. Okay? Yes?
So now gamma depends on K star.
No. No, gamma is equal to 1/2.
But now you can subtract x bar.
What is x bar?
X bar is the mean of the value entries away.
And then?
You don't know this.
Yeah, yeah, I don't know, Krista. Okay? Is that okay? This is a constant, right? A constant.
The thing I don't understand is that if K star is very, very large,
Yes?
then
It's a unit vector. It's on the sphere. On the sphere. Yeah. Okay. So let's move on and let me try to convince you that this is indeed NLP motivated. Okay. Okay. So the example that we found is this one. Let's say that the input sequence is actually made of question and answer, okay? So the set of words has a first part which is a question and then second part which is an answer, okay? And the goal of the task, so given question and answer, so I should say this, we want to predict we want to make some sentiment analysis in the answer part, okay? If the answer contains a positive or negative sentiment. Okay? So we can take an example, okay? I hope that I will have, yeah, okay. So how are you doing, sweetheart? Okay, this is my question. And the answer would be devastated, to say the least. Okay? So each of these words, or token here, are x1, x2, x3, xl, okay? They are all encoded as an RD vector. And I can look at their alignment with K star, okay? So the alignment with K star is the relevant token. So it means that here it manages to catch two types of information, a sentiment, okay, and also the position in the sentence. So the position here in the answer. So we can imagine that all these words here are not really aligned with K star. Maybe sweetheart start a little bit, because sweetheart seems to be like a good feeling. So maybe a bit here. And in the answer, we got devastated. So it should be like very, very anti-aligned with K star. And to say the least, not much about this part. Maybe a bit in the list. Okay? And then we can look at the alignment with V star. Okay? So on this first row, actually, I understand that now my relevant token is this guy here. Okay? So here, G0 is equal to 1, 2, 3, 4, 5, 6. Okay? And if I look at the alignment with V star, so this is possible that here I have nothing, 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 something very positive here, something very negative here, and then nothing, nothing, and negative here. Okay. So then my prediction is going to be given by this. Okay. So Y is going to be a score that is really, really negative here, encoding the bad sentiment contained in the answer. Okay? Is it clear? Yeah? Good. So the features that we like actually in this task are the fact that we have a kind of token-wise sparsity feature that is encountered in practice. Okay, so and we also retrieve some latent linear projections that are inherent to the task, but that has also been seen in practice in attention-based layers. Okay. So okay, so of course here the latent linear projections are given by K star and V star. Okay, so to solve this task, well, there is no, like I would say, like traditional estimator or predictor to solve it, right? So what we can try to do is to construct it by hand. Okay? Okay, step one. Okay, maybe first I should say that I'm going to. I didn't want to use this this notation because for me now, double X will be all the token. Sorry. In this matrix form, okay. LD. So I have my whole sentence here. Organized in this matrix. Okay? So to form a predictor, I could start by assuming that K star and V star are known. Okay? Like strong assumption. So if they were known, what I would do, I would construct this predictor here. So here you see I'm looking at the product between this matrix, so all the scalar products of my tokens with V star, and I just select a little G0x, the index little G0x, where G0x will be the argmax over L of X K star. Okay? Yes? Okay. Do you agree? Because if you disagree, then we cannot go on. Yes? Yeah? Okay. Okay, but you see, I can actually rewrite this in the following way. Okay, this is equivalent. Of course, when I look at this predictor, I have mainly two problems. The first one is that I need to know K star and V star. Okay? And the second one is that I have this non-differentiable part. Okay? Yeah.
Just one question for your argmax. So if t goes to infinity, will you be able to extract the capital J0 with high probability? Is that what's happening?
Yeah, so we can control with high probability the fact that G0 will be equal to big G0, yes.
But indeed, D is large, the dimension.
We do not have make this computation ultimately, but we will see that this is not really important for what's going.
For small d, I think the support should overlap quite significantly, so you shouldn't be able to extract.
Yeah. I agree. But we haven't really formalized it very well in the paper. Okay, step 2.
Don't you need someone so very here because K star can be negative? So
Yes. And what's the problem with this?
someone so very in our marks.
No, but my x will be aligned with K star no matter the direction of K star is. My x that are aligned with K star are the one that I want to select. So this is indeed, look, xg0 is centered at K star. So that should be okay. Yeah. Okay, so let's try to relax a bit this predictor. So let me call it TKV soft. And of course, well, you see me coming, right? I will relax the argmax by a softmax. So I add some temperature here. And of course, I will replace K star and V star by some parameters K and V to be learned. Okay? So I can actually write it in the matrix form. This way. Okay? Okay, and softmax. So lambda is just the temperature of the softmax. So this is just a positive parameter. Okay? Okay, so at this point, I hope you are kind of convinced that this is indeed an attention-based layer. So we have like a proper comparison with traditional attention layer in the paper if you want to see it. But for now, I think we can just believe that this is indeed looking like an attention-based layer. Okay? Of course, we have lost here the queries part, but you can actually show that it's hidden here in the temperature of the softmax. Okay? So we could stop here, but the problem is that when you try to analyze mathematically what happens with the softmax, you have this renormalization in the softmax that make a dependence between all the tokens, and that make the computation a real nightmare. So we need to use a last simplifying step where we replace the softmax nonlinearity by a component-wise operation. Okay? Okay, so my final predictor will be this one, parameterized by K, V, and temperature lambda. I will use the activation function f. Okay. Okay, I should say this, xl transpose x and transpose v, or a way to write it in a matrix form. Okay, so this is a simplification, of course, but you can find some paper, some applied paper, that actually use attention layer with component-wise activation function, and that seems to give and to lead to good performances in practice. So let's say that this is not too harmful to make this simplification for practical purposes. Okay? Okay, and so the R function, just for everyone. Is given like this. And, well, when you look at it, something like this. Okay? Yes. So what can we say about this predictor in terms of its statistical performance? So be prepared, it's going to be short. We cannot say much actually. So first, I should say that the computation of the risk is really tedious. Okay, so I'm looking at the quadratic risk, okay? And with all those assumptions about the distribution of my data, we manage to get almost a closed form version of this risk restricted to the sphere, okay? And we can make a first observation. Is that if we want to say something about the Bayes optimality related to this problem, we can actually just observe that this risk here will be larger than, yeah. Then this, okay, yeah. And therefore this is equal to the expectation of the square of the noise term that I will assume to be equal to epsilon square. Okay, so we know how to bound from below the Bayes risk when we are in a non-asymptotic regime. Okay, non-asymptotic in terms of d or the length of the sequence. Okay, so to say a bit more, we are going to make the following assumption, and this will be considered for the rest of the talk. We will consider that K star and V star are orthogonal.
Inequality, that's really large, right?
Is, sorry?
Sorry, the first inequality in your
Yeah. Yeah, I have too many expectations.
Well, I mean, just because plugging in the K0 is a significant simplification of the problem, knowing.
Yeah, sure. So we are just saying that we are not able to characterize the Bayes risk. We are just able, in a non-asymptotic way, to bound it from below. yeah, this is not much. Okay, so we can show the following proposition, that if you let the dimension d go towards infinity, and you take the length of the input sequence to be a little OD, so it means it can be fixed, but it can also grow to infinity, but not too fast with respect to d. If you take lambda such that lambda square root of d tends to plus infinity and lambda square root of L tends to 0, then we have that the risk of my predictor with these oracle parameters will tend to the lower bound on the Bayes risk. Okay? So it means that the oracle predictor T lambda K star V star is asymptotically Bayes optimal. Okay? So we can, well, this is kind of easy to get an intuition why those scaling are here. You just need to split this part. So you put K star and V star here. You split this part into what happened for G0 and what happened everywhere else. And you will be in the saturating part of the R function, and you will really end with those type of scaling. Okay? So I don't know what I should erase now. So.
Excuse me, before you erase that.
Yeah.
So the reason that you go from step 2 to step 3 is that you don't want to be bothered by the division of the sum of the x.
Yeah, I removed the normalization problem. Yes, but we are limited people, and then we didn't manage to get through the computation. But yes, actually there are some works that manage to handle the softmax, but for now, up to now, we didn't manage. Yeah. But probably. But this is already a nightmare with the ERF activation function to compute everything. Yeah. Okay, and so maybe to close the statistical discussion, we can say something about just the linear model. Okay? So what about the linear model? We can focus on beta star, sorry, which will be the argmin of this risk, okay, where I concatenate all my tokens, okay, yeah, I concatenate all my tokens, yeah, and I just look at the best linear coefficients to predict y, okay? So if I do so, I can show that this risk for, well, I would say risk of beta star is equal to epsilon square, gamma square, minus gamma fourth over gamma square plus L minus 1. And this is true when G0 is uniform over all the indices. Okay, so when my token is uniformly distributed among all the input token. Okay. So of course this is optimal when L is equal to 1. Okay, when L is equal to 1, then actually my model is just a linear model. only have one token, so this token is relevant, and I just have to learn a linear model to predict y. So when L is equal to 1, this is optimal, but when L tends to infinity, I have this risk of beta star that tend to epsilon square plus gamma square, which is actually the risk of the null predictor. So this just shows that, of course, a linear model cannot learn anything in this asymptotic regime because of the randomness of the position of the relevant token. Okay? So it has, the linear model has to spread off all the information everywhere to hope to catch something, and then he just drone everything. Okay? Okay, and so now this is the end of the statistical story, and I have 3 minutes maybe to discuss about what happened when you try to learn the parameter. Okay, so last part of the talk. So I will do training. So I put like big quote around training. Okay. Why? Because we will do training via optimization of the theoretical risk. Okay. So what does it mean? Of course, this is a simplification. Here we should use like an empirical version of it, but we are making, we just choose to use the theoretical risk in the optimization procedure. The problem is still non-convex and non-trivial to solve, right? So what we can show is that we are going to run a projected Riemannian gradient descent, okay? Meaning that we update the parameter k in the following way, as a projection over the sphere of kt minus alpha of the gradient of my risk, and actually the same stuff for Vt, okay, but with Vt in place of Kt. Okay? So this is, here you see that we use a projection of the gradient on the tangent space of the sphere. This is a precaution that we are taking because we actually are able to write the risk, an expression of the risk, only on the sphere, okay, and not everywhere in the space. Okay. So we are almost done. When we look at those iterates, we can realize that there is a submanifold which is this one, sorry. Okay, so this submanifold where you have your parameter k orthogonal to v star, your parameter v orthogonal to k star, and both are orthogonal together, we can show that if our iterates are in this manifold, they will stay there. So this is an invariant manifold for our optimization procedure. So this is good news, but of course, you understand that this manifold requires the knowledge of V star and K star. Okay? Yes, yes, yes. And so to finish, what we managed to prove is the following. If you take lambda t to be like a constant temperature, okay? There exists some bound alpha such that for any constant step size alpha less than this bound alpha bar, and for a generic initialization K0, V0 on this invariant manifold, we have that Kt, Vt given by those gradient descent iterate will converge to plus or minus K star V star. Meaning that despite the non-convexity of the problem, these gradient descent iterates are able to converge towards the oracle parameter that can help you to interpret, of course, your regression task. But the prerequisite to show this is to be on this invariant manifold at the initialization. Of course, you don't know in practice how to initialize on this manifold. So we would like to show, and we didn't manage to do so, that this manifold is actually stable, meaning that if, when you initialize randomly on the sphere, you are close to this manifold at the initialization, and we like to show that it's going to be attractive for the optimization trajectory. We didn't manage to show this, but in numerical experiments, we could see that this phenomenon could happen, but with some careful choice of the temperature during the optimization. Okay, so there is something more to be understood if we want to show the stability of this manifold. And I think I'm over time, so I will stop there. Thank you.
Thank you very much. We have time for a quick question.
Yes.
Do you use the three conditions? If you initialize with K and V that are orthogonal, do they stay orthogonal?
K and V, yes. Yes. Yes, yes, indeed.
But that will not be equal.
Oh, no, sorry. If you do so, you will have some term, some perturbative terms involving the scalar product with K star and V star, so that's why you need to cancel them. Yeah. So we need the three null scalar products. Sorry. Yeah.
But I was just wondering, your normality assumption, I think one of the key purposes is that you have a KL that increases with a certain rate in D. So could you just ditch the normality assumption and work instead directly with a KL assumption, for instance, just to make it more general and not normal?
Maybe we could discuss about it, because I think I don't see the things as you do.
You need the support needs to kind of separate.
Yeah.
Because that KL would be sufficient. You don't need normality. I mean, from normality, you can easily KL.
Yeah, okay, so the normality assumption is kind of nice because we obtain closed form formula with the R function.
Okay, so there might be other purposes. I think one key purpose is the support, which does not.
So thanks again, Pierre, and for all this.
Thank you.